In this lecture, we're going to be talking about broadband access methods. We'll talk about the importance of having broadband access, and then we're going to talk about some of the methods that we use, such as the digital subscriber link, the cable antenna television, passive optical networks, and then wireless local loops. Today's high-speed, high-capacity digital networks serve many purposes in many industries. As an example, for the medical industry, telemedicine is possible, as well as the sharing of MRI data that has to be exact. There's businesses that enjoy high-capacity networks in their supply chain, as well as video teleconferencing with other partners or within their own organization. There's also telework, which has been opened up a new avenue of way that people can actually stay at home and work on many days during the business day. And then, of course, for all of us who love entertainment, we have high-speed television programming in high definition or 4K, as well as gaming that serves our purposes to be able to join other groups of gamers onto a server. However, to gain access to this high-speed network, we have to have a broadband access that allows us entry into the network, that last-mile connectivity that won't be the weakest link. And so, as such, broadband access becomes very important. And we'll be talking about several of the methods that we saw on the last slide. In fact, high-speed access to networks such as the Internet has become and been declared a human rights under the United Nations, under the Universal Declaration of Human Rights, the UDHR. And the goal of the UDHR is to ensure human freedom of expression, economic prosperity for even the most remote areas. Of course, we're pretty lucky in this country because our last mile connectivity has always been available, and there's a lot of ways that we can actually accomplish last mile connectivity, but it has always been challenging. And some of the methods have been through satellite connections, the telephone lines, through cable television, through wireless local loops, and through fiber optics. Now, we're going to be talking about several of them. We won't be talking about the satellite systems, but we will talk about the others. Let's talk about one of the first broadband access capabilities that came around, especially in support of small businesses and residents. It was the digital subscriber line. And the digital subscriber line ran over the traditional analog telephone lines. And of course, the traditional analog telephone lines were unshielded twist to pair. So we used unshielded twist to pair, and of course, that doesn't really give you a lot of bandwidth. And plus the fact that the nice thing that most of the runs between your telephone at home to a central office was essentially 18,000 feet. So that would be to the central office, and this would be the dedicated local loop line that services every telephone. Okay, so if you think about what we had before, if we wanted to get into the internet, we'd have a dial-up modem. The dial-up modem would give us very, very small capacity. Larger businesses could afford a T-carrier connection or a dedicated line directly into the high-speed network. And so that was great for them, but for the rest of us who couldn't afford it and small businesses who couldn't afford it, DSL, dial-up modems were essentially it until DSL came around. And once DSL came around, then we had a lot more capacity. Now, just like many of the other standards that we talked about, DSL is actually a family of standards. And so this table shows that we've got asymmetric DSL, symmetric DSL, very high DSL, high data rate DSL, and then super pair high-speed DSL. What we're going to be talking about mostly are the asynchronous DSL lines. Asynchronous in the sense that there's a separate downstream, which means data that you're downloading from the internet, and then upstream, which represents the amount of data that you're actually putting on or sending up to the internet. And so we'll talk about mainly the DSL, ADSL2, and ADSL2+. So why asymmetric? Well, for most of us, we will download a lot more information from the internet than we will actually post up to the internet. And as such, because we have a limited spectrum when we're using unshielded twist to pair, it makes a lot of sense to reserve most of that bandwidth for the information that we're going to actually be downloading from the internet. So Asymmetric fits the profile of use. Now, there's a couple challenges for, especially when we go into the neighborhoods and try to deliver ADSL. And the first challenge is the fact that we have what we call loading coils that have to be removed. So we're going to have to remove loading coils. And so these loading coils are dispersed about every 3,000 to 4,000 feet out of this 18,000 feet. So you can imagine that there's a lot of loading coils that have to be removed. So what are the loading coils and what do they do? Well, back when there was just all analog local loop lines, we of course used twisted pair, and the twisted pair, as we had discussed in previous lectures, would create capacitance in the line. And unfortunately, this capacitance that was on the line would actually attenuate the signal. So it would run a very short distance before your signal-noise ratio was very, very low. As such, they thought that in order to get rid of the capacitance, they would actually put inductors that were called loading coils along this local loop every 3,000 to 4,000 feet. And so what happened is that would actually counteract the capacitive reactance and therefore less attenuation, and your signal could go much further. And in this case, it could go all the way out to 18,000 feet. So it was a good thing for analog voice grade calls. The only bad thing is the creation of a loading coil plus a capacitor actually created what they call a low-pass filter. And a low-pass filter would only allow low frequencies, and that low frequencies was at the 4,000 kilohertz range. Now, once again, that was fine because, of course, we had an analog voice signal, and we said voice grade was only up to 4,000 hertz bandwidth, and so that was sufficient enough to actually have voice grade communications over analog telephone lines. Of course, if we want to increase the capacity or the bandwidth of the unshielded twisted pair, then we want to go much higher than 4,000 hertz. We're going to have to modulate up to the higher frequencies, and as such, if we have a low-pass filter that cut everything out above 4,000 hertz, then that would mean that we would not be able to use higher frequencies, and we would not be able to use modulation techniques. Another problem that the local service provider would have to take a look at is if there were any analog amplifiers that were placed on the line. If there were, they would have to remove them. So we would have analog amplifiers that would also have to be removed. And especially in the older neighborhoods where the local loop lines have been around a very long time, there have probably been several repairs made on the local loop line, which means that there would be splices. And because of the splices, for analog system, there might be mixed gauge splices. And we know that gauge is the thickness of the wire. And so if we have mismatched thickness of the wires, which means we have mixed match impedance, for a digital signal, we could actually get some reflection on the lines. And if we get reflections, destructive reflections on the line, that means that we're going to essentially have echoes, and we would have a return loss, and then, of course, the signal would be distorted or impaired. So the lineman had to take a look at the splices, how many of them there were, and this would be especially true, like I'd mentioned, in the older neighborhoods. And then the last issue would, of course, be RFI. And there wasn't much you could do about RFI because unshielded twisted pair means that you don't have any shielding. And so any kind of interference could come directly into the unshielded twisted pair. And so that was just another factor that, of course, if you reduce your signal-to-noise ratio because your noise increased, then you're going to have limited capacity that you could actually connect up to through the local loop line. So with all these factors, the service provider would have to make sure that there was sufficient signal-to-noise ratio in order to apply an ADSL line. But not all homes could actually have one because of the fact that there might be some issues with their local loop line. So this was something that the service provider would have to look on a case-by-case basis. So one of the things that we have to worry about when we talk about unshielded twisted pair is the fact that we can have crosstalk noise. So we not only have to worry about RFI from outside the unshielded twisted pair medium, but also the crosstalk between unshielded twisted pair mediums. Because we know that if we have two pairs and they're adjacent to one another, and we send a current which is the signal across one pair, it's going to create electromagnetic signal, which is eventually going to create the same signal on the second pair through magnetic coupling. And so as a result, we have to worry about that. And so we have two, a near-end crosstalk, which is next, and a far-end crosstalk. And so what's the difference between near-end and far-end? Well, near-end, think of the fact that you're talking from the point of view of the service provider. So the near-end would be at the central office. So at the central office, there's this piece of equipment called a DSLAM, which is a DSL access multiplexer. And so this multiplexer is where all of the incoming and outgoing signals are going to go to each of the users out in a neighborhood. And so since they're all bundled up together, then we can say that, well, signals are going to start to couple from one another, and especially the signals that are coming in from the users are going to the central office are going to be pretty weak by the time they get here because they've been attenuated, whereas the signals that are going out are going to be fairly strong, as you can see by these arrows. And as such, you're going to get a coupling, and so the only way that the service providers can actually make sure that they keep the crosstalk in check is to go with what we call a attenuation to crosstalk ratio, or just ACR. So this is called attenuation to crosstalk. Now we know that because it is a ratio, we can turn it into a decibel. And so this is what this formula actually does. It turns this ratio of the attenuated signal coming in from the field into the central office is going to be smaller, and then how much is the crosstalk between all these pairs near the central office or at the DSLAM. And if you there are going to be certain specifications as to if it's this low, if the ratio is this low, then you have to do something about it. So they just watch this ACR ratio just to make sure that the crosstalk between the wires is not going to overpower the attenuated signal that's coming in from the other side. And so near-end crosstalk, because of the fact that all of these wires are bundled together at the central office, is a greater issue than far-end crosstalk. And so let's talk about far-end crosstalk. From the perspective of the service provider, the far-end crosstalk is going to be at the subscriber side. So let's just follow one pair of wires here, and then let's say this is at a house. And so this would be where far-end crosstalk is going to be. Now, of course, if we take a look at this ACR ratio, we say the attenuated strength of the signal coming in. So this is the signal coming in from the service provider over the crosstalk. Well, in this case, we only have one wire coming through, so there's not going to be any crosstalk, and so effects isn't going to even be a problem. But even if we had a business that had maybe two pairs coming in here, now you're going to have crosstalk between the two pairs, but the crosstalk at the far end is not going to be as bad as at the central office, where all the wires coming in from all the subscribers are going to be bundled together. And so far-end crosstalk is usually not considered a really big problem. Now, maybe in a case where you have a very large organization that's all using ADSL, but chances are if you're a large organization, you're going to use another access means. Maybe you're going to have a T1 carrier or even a T3 carrier connected up to your high-speed data network. In this case, it would not be the case. So with far-end crosstalk and near-end crosstalk, near-end crosstalk is much, much worse than far-end crosstalk. Now let's take a look at how we allocate the spectrum across the unshielded twisted pair using ADSL. And so here we'll take a look at ADSL2, this upper chart. And so you can see this is in the frequency domain. And what we've actually done here is we're actually supporting 4 kilohertz of the analog signal. And so this way, if you have a lot of analog phones, you don't have to replace them with digital phones. You can use your analog phone, and this is a choice that you make. And what you would have is a device called a splitter, which would separate your analog signal from your digital signal. Now, if you decided that, you want to get rid of your analog telephones and you just want to replace them with digital telephones, then, of course, you could use the rest of that 4 kilohertz bandwidth. You can use it for additional channels. Now, you can see that right above, in the frequency domain, above the analog part, is the upstream subcarriers. So subcarriers, we're talking about orthogonal frequency division multiplexing here. So we're going to have all of these 4 kilohertz channels that are going to overlap one another, and we allow that to happen because of the fact that they're orthogonal to one another, and they're 4 kilohertz wide. Of course, what that means is that for any data that you want to send up or collect, you're probably going to split your message up into several subcarriers. So you'll be using several subcarriers, which is a good thing because, as we discussed in OFDM, and the fact that the unshielded twisted pair on the local loop line is very susceptible to RFI, OFDM will give us a little bit of RFI immunity, and so OFDM is actually pretty good in this case. And so we have our upstream channels, and you can see that these are channels 6 through 31, and then the higher channels above 138 kilohertz in this case are going to be the downstream subcarriers, and those are the ones coming from the internet, and those are going to be subcarrier channels 32 to 256, going out and using up to 1100 or 1104 kilohertz of bandwidth across the UTP, or across the unshielded twisted pair wire. So you can see with this spectrum that certainly we're going to have a lot more downstream subcarrier channels from the internet than we do upstream subcarrier channels to the internet. When we look at all these subcarriers, we know that we're going to have to modulate each of these carriers. And so we're going to use M-ary quadrature amplitude modulation. Now, with M-ary modulation, we can actually change the level of M depending upon the conditions, the RF conditions, or even the conditions if we have a narrowband interferer and we want to avoid certain subcarrier channels. And so in order to do that, we use smart modems, and these smart modems are going to have the smarts to essentially say, hey, if I have some noise that's hammering a few of the subcarrier channels, I'm just going to take them out. I'm not going to use any of those for any kind of communications until the RFI condition or noise condition improves. And then once they're free of noise, I'm going to start using them again. So with the smart modems, you really can maximize not only your capacity, but then minimize the effect of RFI on your transmission. So how we use this spectrum is called discrete multitone, or we just call it DMT. It stands for discrete multitone. So that's a format that we're actually using. The other thing that we have to think about is the fact that we are on a shared medium. So this is a shared unshielded twisted pair, and we're actually dividing our upstream, our downstream, or our transmit and receive by frequency. And so we can also say that what we're following is frequency division duplexing on using ADSL. Now, as you can see from ADSL 2 plus, really the only thing that we've done is we've extended the frequency of the UTP from 1104 out to 2.2 megahertz. So we've increased that by quite a bit. But we still have the same number of upstream channels. We still support analog as an option. And the only thing we're doing is we're increasing all the downstream capacity coming from the internet. So let's take a look at a few ways that ADSL is actually implemented. We start off with the central office, and of course we talked about the DSLAM, which is the multiplexer. That would be attached to an ATU-C set of modems, usually in a rack. And ATU stands for the ADSL transmission unit. And the -C stands for centralized. And in other words, all the modems that are racked up at the central office. Once it left the ATU-Cs, it would be combined, the digital signal would be combined with the analog voice signal. And so this combination of analog voice and digital signal, and we'll take a look at the case A here, would go to a splitter, and the splitter would segregate the analog call from the digital. So it would be the splitter that was between the 4,000 hertz and above for digital and 4,000 hertz and below for analog. Of course, in order to do this implementation, the service provider had to send a service call technician to actually put the equipment in. And over time, this became kind of a burden to the service provider. So they wanted to save a little bit of money and develop a kit where they would just send equipment to the subscriber, and the subscriber could actually do the installation themselves. And so this was known as ADSL Lite, G Lite. And so same thing, it would come out of an ATUC. And this combined digital and analog signal would then go to the computer, but then in order to get to the telephone, you'd have a microcomputer, microfilter. And this microfilter would just attach to your phone is an actual low-pass filter, which would only let analog signals below 4,000 hertz pass to the telephone. And so you'd have to have a microfilter for every one of your analog phones that you had. And then the third way, and probably the more popular way, is you'd have this combined signal coming to an ADSL router, so this should be included in both of those. And at the ADSL router, it would send the digital signal out to the computers, and then the analog signal, you'd have both the digital and analog signal there, so you'd have to have a microfilter that would filter out the digital signal and then provide the analog signal to the telephone. During the days of over-the-air broadcasting, there used to be a broadcast antenna that would be high on a hill, and it would broadcast its programming, whether it was radio or television. And if you wanted to receive the broadcast, you had to have direct line of sight to the broadcast antenna. Of course, this was not always possible, especially if you were in a mountainous area where the direct line of sight to the broadcast antenna couldn't be made. And so, as a result, say you were in a valley and you didn't have direct line of sight, your programming was going to be very poor. And so back in 1940, individual, John Walsh, came up with this idea of actually connecting a coaxial cable to the broadcast antenna and then stringing the coaxial cable all the way into the area that was not getting really good line of sight reception, and then using that coaxial cable and pumping it into each of the residents and businesses around this area to get programming. Of course, this became real popular because the signal would be very, very good because of the fact that it was traveling through a coaxial cable instead of through the air. Of course, the signal quality over a coaxial cable is much better than the signal quality through free space from a broadcast antenna. So as a result, a lot of the other regions within the country decided they wanted to have really good, clean signals as well, and so cable antenna television became very, very popular. Now, at the time, both television and radio broadcasting was heavily regulated by the FCC, and so the FCC saw cable antenna television as just an extension of the over-the-air broadcast, and so therefore, cable television was heavily regulated as well. And that was the case until the Cable Communications Policy of 1984. And this policy, which was about the same time as AT&T's divestiture, was one to free up some of the regulations of the cable communications industry so that they could be more competitive, offer more innovative solutions. So in this era of deregulation of a lot of industries and innovation of the internet and computers and IC chips, it was the time for the Telecommunications Act of 1996, which we had talked about in a previous lecture. Of course, at the time, if you looked at the cable industry was nothing but a lot of stovepipe companies that were serving local areas. And so each one could not interoperate with the other because of the fact there was a huge lack of standardization and therefore a lack of interoperability. And so the cable industry realized that this was the case, and they came up with DOCSIS in March of 1997. And so DOCSIS stands for Data of Cable Service Interface Specification. And so the goal here was to have a standard interface for all the equipment that we used in cable television, and that by doing that, you could actually interoperate between cable networks. And so you could actually have large regional and maybe even national cable television capability. And so this actually spread out internationally, and so in the ITU-T came out with the Euro DOCSIS in 1998. Now, like all of the other standards that we talked about, there's a family of standards, and the standards are usually changing and evolving over time. And so that's similar to what DOCSIS went through. We had DOCSIS 1.0 in March of 97, followed by a DOCSIS 1.1 in 99, 2.0 in 2001, 3.0 in 2006, 3.1 in 2013, full duplex DOCSIS 3.1 in 2016, and then, of course, 4.0 in 2017. Now, you don't need to memorize this list for any kind of exams or homework assignments, but suffice it to say that this is a way that we can actually implement innovation, technical innovation, into all of our standards, is by having it evolve over time. And it makes a lot of sense because you want to always keep increasing your data rates, meeting demands of your subscribers by innovating new technology into your standard and into your systems. So let's see how the CAT TV actually distributed its signals. And of course, we always start off with some kind of provider end, and we call this the cable provider head end, and the piece of equipment we would call the cable modem termination system. Now, in the old days, the optical signal that would go out to optical nodes that were located in every neighborhood was actually coaxial cable. But today, because of the high data rate demands and the quality of the optical signals that we can actually send, a lot of these are now optical signals from the CMTS out to the optical nodes located in the neighborhoods. And so this is now called a hybrid coaxial system, or what we call a HFC. So this stands for hybrid fiber coaxial. So let's go ahead and write that down. Hybrid fiber coaxial system. So it's a combination of optical and coaxial cables. Now at the neighborhood, we see that this cable, so the optical node would actually change the signal from an optical to an electrical, and then the electrical signal would run on these coaxial cables within the neighborhood with taps going into each subscriber's home. Now, this is a very different architecture than when we talked about DSL, because DSL operated on unshielded twisted pair dedicated lines going individually to each subscriber's home. And in this case, we have a coaxial cable that acts as a shared medium that must go to each one of these homes. And so the big disadvantage here is that, number one, any signal coming to or from the subscriber is going to be on a shared network. Now, the problem with the shared network is that you don't have as much privacy, so encryption becomes very important because all of the data of your neighbors are going to go through that coaxial cable. Number two is the fact that your capacity will go down during certain times. So say, for instance, everybody goes home at the end of the day and they jump onto their internet that's provided by cable television. And so it's going to get very congested if everybody jumps on at the same time. And so what you'll see is that during those high peak times, you're going to have less throughput than during other times. And this is something that you may not necessarily see in your neighbor or in the local area if you're using, for instance, DSL or PONs, which we'll be talking about next. The connection from the CMTS all the way out to each subscriber's CM or cable modem is going to be asymmetric. So you expect to have more download from the internet than upload to the internet, as an example. So your downstream bandwidth, so this would be the downstream bandwidth, could be anywhere from 50 megahertz to 1 gigahertz. And so the channel sizes of the connection is going to be right around 6 megahertz wide. So each channel within this bandwidth is going to be about 6 megahertz wide. And you're going to have to modulate each one of those channels. So we're going to use a M equals 63 up to 256 quadrature amplitude modulation technique. Now let's turn our attention to the passive optical networks, or PONs. Now PONs is a subset of the optical distribution network, which is comprised of the active optical network and then the passive optical network. And we're going to mainly concentrate on the passive optical network. So what we're trying to solve here is, of course, the last mile connectivity. So let's say you have the central office, and of course we know that we have a telephone line, the local loop line, which is going to go to each house. And we've already said that this is going to be about 18,000 feet. And if we want to turn that into kilometers, we just say that this is going to be 5,486 kilometers. We'll use that as a reference. So if we were to use an active optical network, what we're really talking about is having our fiber optic communications. We would have to go through some kind of amplifier. Maybe we have some kind of repeater, and then out to the customer. So obviously, even though you'd have a pretty strong signal, the fact that you have active components that you have to maintain becomes a maintenance issue for the service provider. If you look, however, at a passive optical system, all you have is the maintenance of the two endpoints, one at the central office and then one at the subscriber. You don't have to worry about maintaining any equipment, active equipment in between. So that makes it very attractive. So passive optical networks has been something that companies have been using, service providers have been using to actually get much more capacity out from the central office or the head end or the service provider out to every subscriber. So if we look at a single mode fiber, of course we would use single mode fibers because we want the most capacity and distance we can get. A single mode fiber will typically propagate out to 20,000 kilometers. Now you can see the big difference is that you have almost 4 times as much distance using single mode fibers than you have to if you're just going to replace the local loop line. And so if that's the case, then you could actually split a single mode fiber several times to go to several subscribers and still not lose a lot of signal power. And in fact, with this you could actually support up to 622 megabits per second on a single optical line. So that's the whole idea between passive optical systems, is that you're going to have to run a single mode fiber from the central office out to each residence, but what you get is the fact that you don't have to maintain it. You just place it in the first time and you're good to go. And you provide a high capacity, obviously, and reliable communications to each one of your users. Now, for passive optical networks, there's a lot of different applications, not just the one that we looked at in the previous slide. And so there are different specifications under PONs depending on what the application is. Now, on this list, you can see a lot of different applications. You're not responsible for this, but you should have the idea that there are many, many ways that we could actually implement passive optical networks. As an example, the ITU 1998 version was an asynchronous transfer PON or APON. So we talked about ATM when we talked about wide area networks, and we knew initially that was usually an ATM over a SONET network. And in this case, we could actually place ATM directly over passive optical networks. There's also the broadband PON, and this is the one that we talked about in the previous slide, one that we see like local service providers actually implement today. And so you can see that there's asymmetric speeds. And so 622 was the downstream, 155 megabits was the upstream. And of course, because we expect to have a lot more downloads from the internet than uploading up to the internet, it makes a lot of sense that we have much more bandwidth downstream to provide the asymmetry of our signal. And then there was in 2008, an ITU G984 Gigapon, improving on spectral efficiencies, because remember we talked about spectral efficiencies and how we, with the limited bandwidth we're allocated, we want to use the bandwidth as best we can, as efficiently as we can. And so you can see that the downstream data rates and the upstream data rates increased quite a bit. And then that was followed by a ITU 987, which then called for 10 gigabit capable PON networks. And so this was called XGPON then followed by even a greater one, 40 gigahertz, an NG-PON. And of course, IEEE was going to get in here as well, and they have a Ethernet passive optical network. And so you can see as we go through all of these different standards and different applications that there's different capacities, all taking advantage of fiber optic, especially single mode fibers. Now, this is the architecture of a typical passive optical network that's maybe provided by your service provider to give you optical FiOS-like programming. And so we always start at the service provider, and we have this device, which is an optical line terminal, OLT. And so this device is going to take the electrical signal coming into it, turning that into an optical signal, which it places over a single mode fiber. And so the single mode fiber travels out into the neighborhoods, and you can see that these are passive splitters. So in other words, they're going to split the optical signal passively, and you can see that it splits it off into two for every splitter that it goes through. And since you're going to be splitting the signal in half, we typically say that we're going to lose essentially 3 dB of power through each one of these splits. But there should be still sufficient energy within the optical signal to actually go and reach the subscriber. Now, there's several ways that they can actually connect this up to a subscriber. The first way is what I think Verizon Fios typically does in a neighborhood, and they call this fiber to the premises or fiber to the home. So it goes directly up to the house. They usually will place the ONT, connect that to the side of the house, and it's usually about the size of a small pizza box. That's why sometimes it's just referred to as the pizza box. And so this device, the ONT, will take the optical signal and turn it into an electrical signal that it then sends out through your cable system at home. Now, another way that we could actually send this signal is through fiber to the curb. And so fiber to the curb means that you're going to have now an optical network unit, which is going to connect up to either unshielded twisted pair or coaxial cable if you have coaxial cable from a former coax or cat TV installation. And so it just connects up to that. And so it turns the optical into an electrical signal, follows up through your UTP or your coaxial cable. And then this is called the optical network unit device. And then the last one is, let's say you have a neighborhood or a block that is going to be served by coaxial cable. And so you essentially just do a fiber to the network, go to a box, which is also a ONU, changing the optical to an electrical signal, and then riding on the existing cable or local loop network, and in this case it's a cable network, that will connect and feed into each of the houses. So a lot of ways that you could actually provide passive optical network into subscriber homes. Now, the last broadband access we're going to be talking about is wireless local loop. So in this case, we're going to be using RF frequencies or optical frequencies in free space. So there's a lot of benefits and costs associated with providing a WLL link. First of all, it's pretty easy to actually set one up compared to having dig trenches and then lay down cable. So it's ease of implementation. And in many cases, especially if you're going to try and put cable through underneath concrete streets and sidewalks, it's going to be more cost effective. And so this is really good, especially for locations that lack a proper infrastructure, for cities that are so built up that it would take a lot to be able to dig up sidewalks and streets, and then for communities that have gone through some kind of natural disaster where you have to set up communications very quickly. Of course, there are costs that are associated with this, and one of the costs being the fact that you're going to have to get FCC licensing. So you're going to have to license your frequencies. As we saw before, trying to get an allocation of frequencies for use can be very difficult at times. And then finally, you're going to be susceptible to radio frequency interference and weather. Because you're not guided, you're not shielded in any way. You're just out there in the elements. Not to mention the fact that because you're in a shared medium that's so open, your security isn't going to be as good. So let's add this as our third consideration, and that would be security, and mainly the threat of eavesdropping. So we're going to concentrate on IEEE 802.16, which is Worldwide Interoperability for Microwave Access, or WiMAX. And a lot of you have probably heard of WiMAX in the 4G discussion, but what we're talking about is fixed WiMAX, which is also called Broadband Wireless Access. So it was first approved back in 2001 as just the 802.16 standard. Is a point-to-multi-point standard that operated in the 10 to the 66 gigahertz range. So this is 10 to 66. So quite a large RF range, because we're talking all about RF communications here. Unfortunately, it suffered from high implementation costs and a lot of reliability problems within the designs, and so therefore the initial standard didn't have very much support. And so it went through several different iterations. At one time, this was a combined cellular WiMAX as well, or what we called a mobile WiMAX and fixed WiMAX. But then eventually in 2004, 2005, they broke these standards out into its separate parts. 2004, the 802.16d was going to be the fixed WiMAX, which is going to be the BWA. And then in 2016 2005, the mobile WiMAX, which we all know as 4G. And then they decided to go ahead and combine them again in 2012, and they called this Enhanced WiMAX. They really kind of concentrated on the broadband wireless access capabilities, and this was going to operate just at the 2 to 11 gigahertz frequencies, and is going to describe, as most IEEE standards do, the physical and then the MAC standard. Now, you might think that the standard 802.16 WiMAX is dead because of its failure to capture market share during the 4G competition with LTE, but you'd be far from correct in that, because we still use WiMAX BWA for wireless local loop. It's still a popular standard, plus the fact that 4G LTE and even 5G LTE uses the option of using WiMAX, fixed WiMAX BWA, as a way to backhaul information from the base stations to the mobile switching center. And so WiMAX is here, and it's not going to go away. In this section, we talked about the importance of having that last mile connectivity using broadband access methods. And we talked about the importance of broadband access methods and how it was included in the UN's Universal Declaration of Human Rights document. And then we talked about DSL in detail. And with DSL, we mainly concentrated on ADSL. We said that it had a DMT format that used OFDM, M-Mary QAM, and then FDD, which is frequency division duplexing. And we said that we still had crosstalk issues because of the fact that the lines going out to the subscribers were going to be unshielded twisted pair. And as a result, we had crosstalk issues, but the main concern was with the near-end crosstalk at the service provider. Then we turned our attention to CAT TV, and we said cable TV. We talked about how it originated, but we also said that because there were so many different companies out there that were operating in very local areas, there was no standardization across the cable TV industry. And as a result, DOCSIS helped to standardize the community and make it more competitive with the other communications firms. And then we talked about using optical networks, and so mainly we looked at the passive optical network that used single-mode fibers and how we actually distribute that across neighbors for that last mile connectivity. And then finally we talked about the unguided system, the wireless local loop, which is the 802.16 WiMAX broadband wireless access, and that this was a different standard from the mobile WiMAX that we usually associate with 4G competition with LTE.